In this video, we will talk about the process of calculation of variance, variance, a variance of whether it is a vector or matrix. So for that, let us create a data, hypothetical data. We have n number of observations. So let us take I to be equal to 3 number of observations. And if there are n number of observations, then I contains n number of ones in its element. And our x is going to be, let us take only 1, 2, 3, and the mean is 2. So in our earlier video, we know that if we want to calculate the sample size n, that is going to be I transpose I. And if we want to calculate summation x, this is equals to I transpose x. Now, if we calculate the mean x bar, let us say this is equals to, first of all, summation x, this is equals to I transpose x divided by n is equals to I transpose I. We know this. Now let us see how do we calculate the deviation from mean, x minus x bar. In general term, it is xi minus x bar, but its matrix or vector counterpart, how do we calculate it? Let us substitute the value. First of all, x, this is equals to 1, 2, 3. Let us solve it by the help of example. Minus x bar, that is equals to 2 in our case. So 3 plus 2, 5 plus 1, 6 divided by 3 is 2. And let us write it as 2. This is the vector notation. So let us operate it further, and this is 1, 2, 3 minus, and here it is 1, 1, 1. Let us take 2 common and outside. So this is equals to, now let us substitute their variable form or the vector form. This represents x minus this represents the I, and this 2 is equals to x bar. And this is our general notation, and this is our vector or matrix notation. Now let us further solve it. It is x minus I, and x bar, we know that x bar is equals to I transpose x, I transpose I. So let us substitute that. I transpose x divided by I transpose I, this is constant n. Now if we further operate it, now let us say if we take x common towards our right, then we are left with I minus I transpose I. So the factor, this matrix is going to give us or transform this x into its deviation from mean form. Now the this is our identity matrix, and in our case, if the sample size is n, then the identity matrix should be of n into n order, and for us it should be 3 into 3 matrix with the main diagonal elements 1, other off diagonal elements is 0. So this matrix is represented as M0, and we call it is the matrix that gives the deviation from the mean of any vector or matrix, and this is our vector x. So our M0 or the deviation from mean matrix, this is equals to I minus I transpose and then I transpose I. This is very simple to construct, where I is equals to n into n, and this I contains the ones, n number of ones, the vector that contains n number of ones, and we can operate it. Now let us say this M0 is an idempotent matrix. This is also called as the deviation from mean matrix. This matrix is responsible to give us the deviation from the mean. Now let us see what do we mean by idempotent matrix. We have two properties of idempotent matrix. If a matrix is idempotent, then its transpose is equals to the matrix itself, and if we multiply the matrix by itself, we get the matrix itself. These are the two properties, and we'll quickly prove these two properties for this matrix, deviation from mean matrix. So let me quickly rub this. So we have seen that deviation from mean, this is represented by M0 x, any vector x or any matrix x. Now we are going to prove whether M0, where M0 is equals to I minus I transpose I, and we want to prove that this is an idempotent matrix, meaning thereby they follow these two properties, and we want to prove it. So let us first of all see this first property. Our M0 is equals to I minus I transpose and I transpose I, and let us take its transpose. So this is equals to I transpose, we can operate it individually, I transpose minus I transpose divided by I transpose I and its transpose. So I transpose and this transpose. And we need to know certain properties over here. If AB transpose is equals to B transpose A transpose, we are going to apply this property. So I transpose, if we take the transpose of this matrix, the main diagonals remains the same, and the off diagonals, if they interchange, then also there's no difference. So the transpose of I, this is equals to I itself minus, let us apply this rule to this. So first of all, A, B, and its transpose is equals to B transpose. So the transpose of transpose is the original vector itself, and then A transpose, we get I transpose divided by, if we apply the same property over here, A, B, and its transpose, so this is equals to B transpose, so the transpose of I is I transpose into A transpose, so the transpose of transpose gives the original vector itself. And if we see this, and if we call this matrix is M0, then we get the same matrix. This is equals to M0 itself. Therefore, we found that the transpose of this matrix is equals to the matrix itself. So we have proved the first property, and let us see the second property. Now we're going to rub this. So the matrix that yields deviation from mean, this is an idempotent matrix, and we proved the first property that its transpose is equals to the matrix itself. Now let us go to the second matrix, second property. So we take this and we multiply it with the matrix itself, and let us see what happens. So this is equivalent to writing is M transpose, this is equals to the matrix itself, so it is equivalent to writing this into some matter. Now let us operate there. I transpose I, and then it is I minus I transpose I. And let us use the simple multiplication. First of all, we are going to multiply this with this, and it is I into I is I. It is equivalent to multiplying 1 with 1, it is 1 minus this into this, we'll get the same matrix I transpose I, this is equivalent to 1, and minus this into this, we are going to get the same matrix I transpose I, and minus minus plus, first of all this one I transpose divided by I transpose I into, again this, it is I transpose and then I transpose I. And if we said it is I minus I transpose I minus this same value plus, and for our convenience this is I transpose I, it is equals to n constant, because we know that I transpose I equals to n, it is constant, we can take it outside, and we can cancel this with this because this is also n, I transpose I equals to n. So if we cancel them out, so let me write n for this I transpose I, let me write it as n because it's constant, and we can take it to this place, n into, then we are left with, so this much we have written it as n, and we are left with I, and this part I transpose divided by, and for this I know we can write n for the both or any one of them, so let me write it as n to this part, and we are left with I transpose, so it is I transpose I, and we can cancel this. Finally, if we say is I transpose, and then this minus I transpose I, and then plus we are left with I transpose I, and let us see, we can cancel either this with this or this with this, any one of them, and if we cancel it, we are left with I minus I transpose I, and this is the same matrix that we had started with, it is M0. So we see that the transpose of this matrix, deviation from mean matrix, and when we multiply it with itself, the transpose of this matrix with itself, this is equivalent to multiplying the matrix with itself, and this resulted in the matrix itself. So this is the second property. That is why we can conclude that if both of these properties were fulfilled, we can say that the deviation from mean matrix, this is an idempotent matrix. Therefore, we can write m0 to the power n also should be equals to m0. If we multiply it, no matter how many number of times, we will end up in the same matrix. So deviation from mean x minus x bar, this is a general notation, and in matrix term, this is equals to x minus x bar. They are the vectors, and ix bar, and this is equivalent to m0x, and where our m0 is equals to I minus I transpose I. We know this result. Now we know that the variance of x is the general formula. This is equals to summation of deviation from mean its square divided by n minus 1. Now we know to calculate in matrix form, we know to calculate the deviation from mean. So to calculate the equivalent of x minus x bar whole square, so this is equals to, in matrix term, this is equals to x minus I x bar transpose it, transpose x minus I x bar, because if the deviation from mean, if we have a vector having deviation from mean a minus mean is equals to, let's write it as x bar, b minus x bar, and c minus x bar. If this is our deviation from mean, like x minus x bar, then to calculate the sum of its square, we simply take the transpose of it, and then we multiply it by itself, like a minus x bar, b minus x bar, and c minus x bar. And when we, this is the transpose, and when we multiply it by the vector itself, c minus x bar, then the result, this is equals to a minus x bar whole square plus b minus x bar whole square plus c minus x bar whole square. And this is equivalent to summation of these. They represent the observations of x I minus x bar whole square. So we use this. Now we can replace this with this result m0x, and we know where m0 is equals to this matrix over here, and its transpose divide, and again into, this is again m0x. They are in their this x is the vector, column vector, and m0 is the matrix, n into n matrix, which we can calculate using this formula. Now let us again use this property, matrix property, E into B transpose is equals to B transpose A transpose, and if we use this, we will get it as X transpose, first of all B transpose, then after A transpose, M0 transpose, and we don't need to do anything, we simply write it. And if we compare this to, we know that X transpose, M0 transpose is the idempotent matrix, the transpose of this is equals to the matrix itself, and further, if we multiply it with itself, we get the same matrix. So this is equivalent to taking the sum of the squares of the deviation from mean. Now if we divide this by n minus 1, we are going to get the variance. So to divide it by n minus 1, we know that I transpose I equals to n, therefore I transpose I and minus 1. This would be equals to n minus 1. So to sum up, what is the variance of, let us say, first of all, let us treat the vector x. This is equals to summation of x minus the general formula x minus x bar whole square divided by n minus 1. Now its vector counterpart, this is equals to the vector transpose and then m0 and the vector itself, and we divide it by n minus 1, that is equivalent to I transpose I minus 1. So if this is true for this vector x, this is true for any vector, whatever its name. Maybe let us say we have a vector called k, and this is of order, let's say 10 into 1. It means we have 10 number of observations. So how do we operate it? So we know that we can calculate this, but how to define m0? To define m0, first of all, we will have to write m, and we will have to write 1, 1, 1. So this would be of order 10 into 1. So we will have 10 ones is the elements. We are informed with I. Then after, we need to create identity matrix of order 10 into 10, because our vector it is of 10 into 1. So 10 into 10, where the main diagonal elements, it contains 1, other off diagonal elements, they are 0. Then we construct this m0 matrix. M0 matrix is equals to I minus I transpose I, and this should give 10 because our sample size is 10. And then we simply calculate the variance of k. This is a vector k. By using this formula, we take the vector k and then we multiply it by this m0 matrix and k transpose k, and then we divide it by I transpose I. This is our n, and we minus 1. We are going to divide, to this particular example, we are going to divide it by 9. So once we calculate it, it is very simple. Now let us say this is the case of the vector. Now let us see if we have the matrix. The matrix consists of so many variables or the vectors. So let us say we have a matrix A and that contains 5 variables, x1, x2, all the way to x5, and they have their observations. So this is a matrix. So if we have n number of observations, then this matrix is of the form n into 5. So in this case, we are going to get the variance and covariance matrix. Variance or covariance matrix of matrix A, this is again equals to matrix A transpose and then M0 A trans A, and we divide it by I transpose I minus 1. So how do we construct M0 in this case? So M0 is equals to I minus I transpose I, and this is an identity matrix of order. Let us say if we have n number of observations, then this should be of order n into n, and our matrix vector with ones, so this should also contain n number of ones as an element, and then we write it I minus I transpose. So how do we calculate I transpose? We simply take up to n number of observations and its transpose up to n number of observations, and if we multiply it, we will also get n into n matrix. Basically, this all contains 1, 1, 1 is its element. So in that case, we are going to, if we operate this formally, then in that case, we are going to get, so this is a matrix, and in the main diagonal elements, let us confine with only 5 vectors. So in that case, we are going to get the variance of first, second, third, fourth, and then fifth. And these are the covariants. So let me write it x1, x2, x3, x4, and then x5. So the main diagonal elements, they are going to give us the variance, and the off diagonal elements, they are going to give us the covariance, because the interaction is possible. This is x1, x2, so sigma 1, 2 square, and this is equals to sigma 1, 3 square, and so on. So this is it for this tutorial. Thank you very much for your time. Thank you very much, Econometrics Melody.